Yes, I will be telling you today about a spectrometric and spectroscopic analysis of two illuminated manuscripts from the 15th and 16th centuries. We worked on this over the summer for part of it, and then also just at the second half on winter term, so new stuff. Okay, so what are illuminated manuscripts? Put very simply, they are handmade decorated books made out of parchment or animal skin rather than paper, and decorated with a range of colors of pigments and inks like the one you see here. Many also have gold leafing, like that, which is what makes them illuminated. So you may have seen these in textbooks, in museums, and wondered, how do historians learn about these objects? Where do we know where they came from, their history? And there's many ways we can do this. We can learn from their text, so what language is it in? Is it in German? Is it in Latin? What is the subject material? Is it religious? Is it secular? It's probably not secular. What's the structure like? Is it large, meant to be kept on an altar in a church, or is it very small, like something you carry around with you? What is the style like? Is it really elaborate, like this work here, or is it more simple, like the two manuscripts that I worked with? There's also other ways we can learn about them, more scientific ways in terms of pigment composition and parchment type. And so this is the area that my research is focused on, is identifying these materials. So I want to kind of walk you through the two manuscripts that I have been able to work with, and this is the first one here. It's very small, as evidenced by my thumb for scale. And so this is what's called a book of hours, and it is the property of Dr. Ben Tillman in the art history department here, who so kindly let us use it for research. And books of hours are composed of two primary sections. The first is a calendar of saints' days, which would tell you when each saint's particular day was, when you should have a feast, when you should pray to them, and then the hours of the Virgin. So these are prayers and psalms dedicated to the Virgin Mary. And so this was meant to be carried around with you, maybe literally in your pocket, and pray with at certain times of the day. So we know that it is of French origin, and we're also pretty sure that it's of the 15th century. So this is right at the end of the Middle Ages. And besides these vague historical facts, we also know something chemically about it. Karin Sullivan, a previous student of Allison's, did work and figured out that the black ink, like in the text there, is iron gall ink. And she also determined that the red pigment, like this up here, is mercury sulfide. What we did not know coming into this is what the blue pigment is, like in this initial here, or what animal was used to make the parchment. All right, so here's the second manuscript that I worked with, and it was donated by the Nelson family, Lawrence alumni, and this is the first manuscript in the collection, and so it's called Nelson 1. And it is larger, as denoted by Allison's hand this time. And so this is also, though, a liturgical manuscript, so religious material, but it does contain pages of music, which is pretty cool. And it is possibly of Southern German origin, and it is a little bit later, of the 16th century, so now we are in the early modern era. And so this was new to us. This came after Karin had left, so we don't know what the black ink is, we don't know what the red ink is, we don't know anything about it. But we also don't know, like the first one, what the blue pigment is and what animal was used to make the parchment. Okay, so what were the popular pigments and parchments that were even being used during these time periods? Because while I was shooting in the dark, it wasn't completely in the dark. And so the popular blue pigments that were used were two mineral-based pigments, so these are stable inert compounds that would be ground up and mixed with some sort of binder that you could then use to write with them. And the first one is ultramarine, which comes from the mineral lapis lazuli. And so this was the really fancy, really expensive one. As pricey as gold. You really only used it if you had a lot of money, or maybe you just wanted to decorate the Virgin Mary's robe, or perhaps a saint's robe. The other one that was very popular is Azorite, which is, again, another mineral-based pigment, copper-containing. And this wasn't cheap by any means, but it also wasn't gold. So this was pretty common. And then the popular pigment or parchments that were used in both France and in Germany were cow, sheep, and goat. Some weird stuff can get in there, but that's primarily what I thought I'd be looking for. So, part one, I'm going to separate this into first the pigments and then the parchment. So part one is pigment identification. And so my first research question is, what blue pigments were used in each of these manuscripts? And this seems like a simple question, but there is the caveat of how can we answer it without harming the manuscripts? Because there are definitely ways to do this where I could cut off a little section, I could scrape away at that pigment, and I could go from there. But this is Ben's, we don't want to hurt it. Also, it's old, so it just makes sense not to. And so the answer to this dilemma was Raman Spectroscopy. So what is Raman spectroscopy? I'm going to walk you through it pretty briefly using this simple model here, where you can think of the white box as whatever sample you're trying to identify, and then the two blue circles connected by a spring as the vibrating molecules within that sample. So Raman spectroscopy is a vibrational spectroscopy technique, and the first step is to shine some sort of incident radiation at that sample. And this is monochromatic, so a laser, and there's a couple things that can happen when the light hits the sample. The thing that happens like 99.999% of the time is that your laser hits your sample and that light scatters off at the same wavelength as it went in. So if you're using a 532 nanometer laser, most of the time the light is going to scatter off at 532 nanometers. But we don't care about that. What we do care about is the very, very small percentage of the time where you shine your laser at the sample and it interacts with the vibrational modes of the molecule in a way that results in a slightly different wavelength coming out. This might be slightly higher, maybe slightly lower, but in either case, it's not the same as what it went in as, and that's called Raman scattering. So this is just a cartoony example of the data output that I would get if I was doing Raman spectroscopy. On the y-axis is intensity in arbitrary units, and then the x-axis is frequency or wavelength in inverse centimeters. And so what I would see are peaks, and this is called the Raman shift. So how I was just talking about how most of the scattered light is going to be Rayleigh scattering, where it doesn't change. You can think of that peak as being at 0. And so the Raman shift is designating those slight changes in that wavelength. And the frequencies of each of these peaks can be used to match known samples, standards, previous literature to look and see what your sample is. So that's all well and good, but those aren't the only things that can happen when you shine a laser at something. First of all, so you can get your Rayleigh, you can get your Raman, but what you can also get is fluorescence. And fluorescence is great for some people, and you care about fluorescence, but for me, it was obnoxious and I did not enjoy it. And so fluorescence is not the same as Raman scattering. This is electronic excitation where those electrons in the molecules are being promoted, they're decaying, and they're releasing photons. And those photons are hitting the detector and masking this super weak Raman signal because it's not very strong. And so while I would love to see something as beautiful as this, which, mind you, this isn't even taking into account noise, what I would often see is something more like this. And so you have this wave of fluorescence that's, yes, I can still see my peaks, but if you can imagine if this is not a pure sample, if there's other things going on, it might be hard to tell what you're actually looking for. So keep in mind, as I'm showing you methods, as I'm showing you results, this is something that I fought continuously. So here's my setup. This is the confocal Raman microscope that I used to use this method. And on it is the book of hours in its little protective cradle held back with linen straps to keep the pages down because everything that we did was about safety. So we didn't want to rip the manuscripts, we didn't want them to fall off, no harm could come to them. So the larger manuscript, Nelson 1, didn't require a cradle, it was pretty sturdy, it could fit, so we just rested it right on the stage, which is the black thing there. In either case, we used a 532 nanometer laser, so green, and we used the 10x objective, and this allowed for a nice clearance between the objective lens and the page of the parchment, so we weren't scraping anything when we went in. We used 10% laser intensity. This was just in case of the pigment being photosensitive. We didn't want to just create a crater, which is possible, as I found out with indigo, not connected to a manuscript. And we used a 5-second acquisition time with 20 accumulations. All that means is that I took data for 5 seconds at a time, 20 times over. And then whatever spectra I would get, like the example I showed you earlier, I would compare the peak values to the literature to see if I could identify my sample. All right. So, pigment sampling locations, I sampled blue pigments, many different pages of these manuscripts, and so the results I'll be showing you today are just representative of the same conclusions that I made from wherever I sampled. And so over here we have the book of hours, and this is folio 20V, which all that means is the front of page 20, back to page 20, just kidding. And I sampled from this lovely initial J here on that blue pigment. And then for Nelson 1, this was folio 89R, or the front of page 89, and I sampled from this little guy over here. And just to give you an idea of what I'm actually looking at when I'm focusing the Raman on where I'm going to take my data, this is what the blue pigment looks like under the microscope, so really gorgeous. All right, so results already. I am going to spoil you right away. It's Azorite, and So this is just like you saw before in my little cartoony example. We have intensity in arbitrary units on the y-axis, so that's why there aren't any numbers. We have the Raman shift on the x-axis. And then this blue line here is a spectrum that I took of known Azorite pigment. So this is just plain Azorite, not mixed with anything, just on a slide. And so you can see that there's this really big peak here at about 400 and then some other stuff going on. And so while I was taking spectra throughout the manuscripts, I was looking for those markers. I was looking to try to sift through all the fluorescence and all the things that was happening to find peaks that I could match to something like this. So here are the two spectra that I took. The one on top is in red, and that is for the Book of Hours. And then the one in the middle in black is for Nelson 1. So big one, or little one, big one. And as you can see, they look remarkably similar. So these two have almost identical spectra, and what immediately sticks out to you are we've got some matches here. So we've got this first one at 249 inverse centimeters, this beautiful one at 401, and then that guy over there at 1096. Great. So this was very exciting. I was like, hey, there's some Azorite, and you may be wondering what this junk is, and that's exactly what it is. It's not Azorite, and so doesn't really matter. So again, these are manuscripts. We've got parchment, we've got dirt, we've got people's finger oil. There's lots of stuff happening, and so all that is not Azorite. So great. These three peaks that I found, 249, 401, and 1096, all also happen to match literature values for people who were taking spectra of Azorite in other works of art. So that's wonderful. So I felt pretty confident in identifying the blue pigment in both manuscripts as Azorite. This makes sense, both in terms of the perceived quality of these manuscripts. So they're relatively simple in comparison to that first elaborate example that I showed you. Probably not super expensive. And it also matches the time period. So Azorite was very popular, Middle Ages, early modern era, and so the fact that I found it means, hey, this probably isn't a fraud or something. So that's pretty great. Okay, part two. I'm gonna force myself to pause here. So I'll breathe. All right. So part two is parchment identification. So I did all the pigment stuff this past summer, and parchment, this work is pretty recent. We really did the bulk of it over winter term. And so let's get into it. So my second research question was what parchment type was used in each of these manuscripts? And once again, the caveat is how can we answer it without harming the manuscripts? And so this time, the answer to that dilemma is PVC, eraser, collagen extraction, and multi-tath MS. So, great. What does that mean? So, when I'm talking about parchment analysis, what I'm talking about is identifying a component of that parchment, which is the component that's found in animal skin, and that is a protein called collagen. So animal skin is primarily made up of this protein, and that is the thing that I'm trying to isolate. And so how can I do that? Well, first, I want to give you kind of a layout of what this is like. So if you're not super familiar with proteins, protein structures, basically it's like a little set of nesting dolls where you have the big one on the outside and then the little ones form the more secondary, tertiary, smaller structures. So collagen fibers are these big guys here. So you can think of this as a bunch of collagen strands all together. And this is what that parchment is made of. And then as you go down to its basic components, you get to amino acids, which are what makes protein protein. So just as how nucleotides are the code for DNA, amino acids are the code for proteins. And so what I want to get at is the amino acid chains. That's what I really care about, because that's where I'm going to find the slight differences between species. But before I can get to any of this, I just have to get this big honking thing out of here. So how do I do that? And so step one is to extract those big fibers before I can get to the amino acids. And so this, the whole purpose of this parchment analysis was because I found a paper by Dr. s0krzfSN, who is at the University of New York, and she developed this really cool technique just in 2015, so really recent, that allows you to extract those collagen fibers without cutting a piece out of the page, which is how everybody's been doing it. And that is using PVC erasers. Yes, this is just an eraser. This is what you use in art class. This is your good old polyvinyl chloride. And so these are used in the art conservation world, so it's not a crazy leap because they are used successfully to clean objects, clean manuscripts, get that dirt off without harming the work. And so Dr. Finneman's team was like, hey, who's to say that if this eraser is getting off dirt and other things from the surface without harming it, who's to say it's not getting those loose collagen fibers off of that surface? And it turns out they were right, because when you rub PVC erasers against the surface of parchment, you generate an electric charge, kind of how you do when you rub a balloon against your hair. And that those electrostatic interactions lift the loose collagen fibers from the surface of the parchment, attracting them to the eraser. And so in all of your eraser shavings, you get little curled up pieces of collagen fibers. So this is great because it's stable. So what her team actually ended up doing was sending little tubes, gloves, paper to a bunch of different museums and universities, and so they could do this themselves. And it's something that looks like this, where they rub the eraser on, collect their shavings, and then send it back to her. And what else I found absolutely hilarious was erasing history. Yeah, we had a good minute over that. So great. So this is how I got those big collagen fibers out. But now my goal is to get to the amino acids. And to do that, I need to digest the fibers. Okay, so I've got my eraser shavings, and now I need to mix them with a solution that contains an enzyme. And that enzyme is called trypsin. And trypsin is a protease enzyme. And it sounds scary, but all it means is that it is able to go in and cut bonds, to cleave bonds between amino acids. So you're cutting these long chains of amino acids into smaller chunks that are called peptides. And so I would incubate the eraser shavings with the solution at 37 degrees for 4 hours, and during that time the collagen fibers would unravel and the trypsin would be allowed to come into those amino acid chains. And so the cool thing about trypsin is that it's not cutting willy-nilly, it's not going everywhere. It cuts primarily on a certain side, the carboxyl side, of 2 amino acids. Those are lysine and arginine, with the 1-letter codes K and R. And so, if you can imagine, different species are going to have slightly different amounts of each of these 2 amino acids. They're going to be in slightly different locations. And so, because of those differences, you're going to end up with unique profiles of each one. And to help you visualize this, just think of this as just a random link of amino acids. So each one of these letters is an amino acid. They're all bonded together. So during, and here's lysine and arginine. So during this digestion process, the trypsin enzyme would come in and it would move along the strand and make cuts at those particular locations. So we could go from this big long chain to individual chunks. And these chunks are going to be specific chunks because of those differences between species. So now we have peptides, chains of amino acids that are of specific lengths, and this is called a peptide fingerprint. And this is what allows me to differentiate between species. Okay, so now I've extracted those fibers using the eraser, I've digested them, so I've cut those amino acid chains into small chunks that are depending on the species. How can I analyze them? And this is where MALDI-TOF-MS comes in. And that is a lot of letters, and the first chunk of those letters stands for matrix-assisted laser desorption ionization, which helps a lot. And TOF is time of flight, and MS is mass spectrometry. So I will walk you through these, do not worry. But I do want to make a note here, we don't have one of these, and Lawrence does not have one. So if you have however much that costs, I can't imagine how much that is. If you want to buy us one, please do. But because we don't have one, we had to send our samples to UW-Madison. So I wasn't able to do this directly. We had some help from some great people at UW-Madison. So MALDI, matrix-assisted laser desorption ionization. What does that mean? So after I've digested my fibers, I have them in a solution, I ship them to Madison, and then they would mix that solution with matrix solution, which is a fancy name for an even fancier solution that looks something like that. And so then they would be pipetted in very small amounts onto this metal plate. So what does this matrix solution do? What's its purpose? Well, after you mix them together and you put them on the plate, you allow it to dehydrate. And as this mixture of solutions dehydrates, it crystallizes. And so now we have this elaborate crystal structure of your matrix solution, and in it are those trapped peptides, which we want to identify. So the first step in this analysis is another laser. So we shine a laser at each of these small spots of solution, and what happens is that energy creates this plume of vapor. So these molecules kind of rise up like a volcano. And as this is happening, each one of these droplets represents a mixture of vaporized matrix solution, but also the peptides that are trapped in there. And so in this big event, some of the protons from the vaporized matrix solution are going to protonate some of the peptides. And so some of your peptides get a positive charge. And this is going to be useful in the next step, which is time of flight. So time of flight is the method of separation for this technique. And so after we have hit the laser with our sample, we have this plume of vapor, our peptides have become charged. Now we introduce an electric field. And this electric field gives all of the peptides the same amount of energy. But if you'll remember, trypsin, when it's cutting up, none of those chunks are going to be exactly alike. They're going to have slightly different masses. And because they have different masses, the smaller ones are going to travel faster than the larger ones when given the same amount of energy. And so this is the method of transportation. I can go back and do it again, maybe? And so all of these peptides are going to hit the detector at a different time. And so that detector is a mass spectrometer. And that's the method of detection for mass. And all mass spectrometry is doing is it is determining the mass to charge ratio of each of those peptides, and then the data output for this is a mass spectrum, which looks something like this. So we have intensity, again arbitrary units on the y-axis, and then the mass to charge ratio on the x-axis. And each of these little sticks represents a peptide mass, and the conglomeration of all of those can be used like a fingerprint to identify species. So the lighter masses are going to be on that end, and the heavier masses are going to be on that end. And just to make a note, when I say heavy, I mean really heavy, because these are proteins. So this isn't your organic lab GCMS experience. This is like from maybe 500 or so mass to charge ratio to up to 10,000. So these are really heavy. Okay, great. So now we've got our mass spectra. Now what do? And again, you compare to literature. So analyzing these mass spectra is a method called peptide mass fingerprinting. And because everything is specific to particular animal species, I was able to compare it to this great publication done by Dr. Michael Buckley in 2009. And so he did a similar collagen analysis for tons of species. So yes, we're talking cow, sheep, goat, but we're also talking like manatee, ostrich, things that you're much less likely to find in a manuscript, but are still pretty cool. And so I was able to look through that database and try to match my mass spectra to what he found. So the samples I collected and analyzed were one from the Book of Hours, one from Nelson 1, and one from known cow parchment, which we bought from this cool company called Pergamena, which makes parchment just as they did in the medieval era. So same exact process. So that's pretty cool. So that was our standard. And I do want to point out that, yes, this is preliminary. We didn't do any replicates. This whole procedure is theoretically pretty expensive, although I don't think we've paid for it yet. And so we couldn't just go sending a ton of samples in without really knowing if what we were doing was working. And so also when I show you the results in the next slides, I'm also only going to be showing you a part of the spectra, because proteins are huge, there's tons of masses, it's super overwhelming, so I'm only showing you a labeled subset that represents the main trends that I was seeing. So the first spectra I'm going to show you is from the Book of Hours. There it is. All right, so we have intensity again on the y-axis, arbitrary, and then mass to charge ratio on the x-axis, and for this particular range I'm showing you is from about 2,000 to about 3,200 or so. And you don't have to spend some time squinting at these numbers. Just remember we've got this collection of 3 on this end, which are early 2000s, like all of us. Not all of us. And then this grouping of 3 in the middle, which are about 2,700, and then these 2 on the end, which are approaching 3,100. So remember those groupings. So now for Nelson 1, if you can see, this is looking really, really similar, almost identical. We have a grouping 3 here, early 2000s, grouping of 3 here, 2,700-ish, and then the 2 on the end approaching 3,100. These are almost identical, if not actually identical in some cases. And then the known cow parchment, once again, these 3 in the beginning, about the same numbers, these 3 in the middle, about the same, 2 on the end. Okay, so what this looks like is that each sample's fingerprint looks really, really similar, if not exactly similar. There's a bit of shifting in those mass to charge ratios, which may be due to some sort of instrumental drift, we're not sure. So there is a likelihood that these data are telling us that these things are the same. But we can't rush to any conclusions because only one of those peaks, the one at about 2100-ish, matched anything from Buckley's data. So, and not only that, but that's found in cow, sheep, and goat. Really helpful, really great. Yeah. So also, even though they may be showing us the same thing, we have to be careful when making assumptions because similarities between peaks don't necessarily mean that the same animal was used because there are often very minor differences between species, and cow, sheep, and goat happen to be species that are very close. So besides that, I can hesitantly say that, okay, ours match, but they don't match the literature values, so what's happening? And the answer is we don't know. We have no idea. So I can rule out any obvious contaminants, and by obvious I mean keratin, which is a protein found in human skin. And so the peptide masses for keratin were not there, so it's not like I was sampling myself 3 times. I've been in communication with Dr. Pigment, who has been generous enough to even talk to me, and it turns out she's using the same standard. So the cow parchment that we purchased from Pergamena, she used, which is great, and it also tells us that if her numbers for cow parchments and manuscripts were correlating with that standard, and ours do too, but between us we're not the same, then this is probably some kind of instrumentation experimental error that's happening. And so what Dr. Fidement has recommended and what I've been doing is I am in communication with UW-Madison. This is probably an issue of we don't have this instrument on campus. We don't know exactly what's happening. So I'm asking questions about how are you calibrating it, seeing if there's anything there that could be going on. So communication is definitely something in the future. So good chance that both manuscripts are cow, but we're not agreeing with literature values, so we need more data. All right, so summary and conclusions. The pigment, I've confidently identified the pigments of both manuscripts as Azorite, and the parchment may or may not be cow for both manuscripts. Future directions, obviously parchment analysis. This is the area where hopefully future students will really work with. Replicates are the next goal, and also working out details with UW-Madison. How exactly are they calibrating this instrument? How often do they use this instrument? Is it well kept? Also troubleshooting the procedure if necessary. There could be something that I'm doing wrong that I haven't found yet. But besides all this, we are also hoping for some kind of future collaborative exhibit with this manuscript because there's a lot of cool things that we could do with it. A history student could talk about the history, somebody could translate the text, somebody could play music from the pages of music, and then we could have my data up there as well, and so it could potentially be this really cool thing, which I would love to see happen. And also more pigment and parchment analyses for the other manuscripts that have been donated and that are part of the Nelson collection. Okay, so I need to acknowledge many people. First, of course, is Dr. Fleshman, who has been so helpful in this. Dr. Martha Vestling, who was our contact at UW-Madison. Professor Ben Tillman, who's allowed us to use his manuscript. Professor Dave Hall for running 680 and for all of his help in all stages of this process. For the chemistry department, for everything. For the Lawrence University Senior Experience Funding, which allowed me to do anything with parchment at all. And Daniel Martin for allowing me to run to him with, dangerous acids and glassware issues and things like that. All right, thank you very much. Any questions? Lauren?
Just out of curiosity, before you used the Raman, did you by chance ever try to, get rid of the junk by using a PVC eraser?
I mean,
you said you clean it off.
Yeah, but that's to clean off dirt, and it's not just dirt, that's all that other stuff in the spectra, because it's the parchment itself, there's a lot of things going on, and I also wouldn't feel comfortable probably rubbing the PVC eraser over the pigments. Excellent. Michael or Issa?
Okay. Is there a benefit to analyzing the collagen content, or could you theoretically look at other extracellular matrix proteins that are in the skin?
I don't know what other extracellular matrix proteins would be there. And even if they are there, collagen is the only one that I have any sort of database on, anything to compare to. So rather than just kind of an identification study, that would be like, first let's create a database to study,
Right.
which would be pretty complex, but possible. Is that?
I noticed in all of your MS data that there are a lot of other peaks too. So did you choose to point out the peaks that you knew were consistent between the different ones, or like why did you choose those peaks to point out?
Yeah, that was honestly just based on visual stuff. This will take a while to go back. But all the peaks that I didn't label also matched or were very, very similar. So yes, I didn't label them, but that was more for the benefit of it's absolutely maddening to try to look at all the numbers up there together. But yes, most of the peaks, if not all of them, and a lot of the if not all had to do with like this one has a pretty bad signal to noise ratio. And so from what I could tell, there weren't any obvious differences between these spectra besides the little variations that may be due to some sort of instrumental fidgeting. Yes?
I had another question. Just how did you find out all this background information on the manuscripts? Like, was that your own looking into it, or?
Definitely not. Ben teaches a class on manuscripts, and so I think that a lot of the information we have, some of that comes from a student who wrote a paper, an essay, on the Book of Hours, and then others of it just comes from Ben himself, from his knowledge of how this has been passed through his family. For the Nelson manuscript, we know less about it, and that's being looked at by Eric history students. So that background information, that credit totally goes to that department. Yeah.
What made you choose cow as your standard? Did something hint?
Yeah, so Karin had looked at the Book of Hours before, and there are ways to kind of give a pretty good idea of what the animal is just by looking at the pattern of hairs. And so it's not like a super solid method, but it gives you a pretty good idea. And so from what she did with that previously, she thought it was a cow. And that was also the animal that was most frequently used, so it was kind of the best bet. She had also ordered cow parchment from Pergamena, so we had it lying around. So convenience. Yeah.
Let's thank the speaker again.